Today, so I'm going to talk about the neutron-star merger in numerical relativity, and I would like to show you that now so numerical relativity is the predictability for neutron-star mergers. And this is the outline of my talk. So after brief introduction, so I'll summarize what is neutron-star, which is the main topics in this talk. And then, so in this neutron-star, we have to eject the matter from neutron-star merger. And then, so in section 3, so I would like to summarize what is the mechanisms for ejecting matter from neutron-star merger. And then, so in the fourth topic, so I just this some demonstration of the current status of numerical relativity. Actually, so for neutron-star merger, we have to follow the merger process for a very long time scale, but now it's possible to do. So then, so I would like to demonstrate such a cutting-edge numerical relativity simulation, which was achieved in the last 3 or 4 years. And then, so using such a numerical relativity results, I would like to guess what happened in GW70 or 70. So I would like to give you some my idea for time series of the process or post-merger process. And then, so I would like to conclude. In the introduction, before going ahead, so I would like to summarize the one-page summary of the numerical relativity. Anyway, so numerical relativity is an inevitable tool in gravitational physics and astrophysics. At least there are 3 important topics in numerical relativity right now. One is, as you know well, so for preparing the theoretical template of gravitational waves, numerical relativity is essential, and as you know well, that so this in particular for predicting the gravitational wave forms from the black-hole merger, numerical relativity plays an important role, and so also so numerical relativity template is has a great success for detecting gravitational wave and for analyzing gravitational wave from binary black-hole merger. And also, numerical relativity plays an important role in modeling electromagnetic signals of high energy phenomena like neutron-star merger and stellar collapse and supernova and so on. And also, nowadays, so numerical relativity is quite popular in just for gravity. So, so nowadays, in particular in the European people, there are many people working in the numerical relativity in the alternative theory of gravity. So I mean that, for example, they employ the scalar tensor theory and some gas bond theory, something like this. Anyway, so now so numerical relativity is just expanding to many fields. But today, so I'm going to focus on just on neutron-star merger. Then, so why? So this is one page, the second page of the numerical summary. And then, so why? So I said that numerical relativity has a predictability for neutron-star merger. The reason is that now, so we have had this community have had great success in the last 20 years. And then this is the equations to be solved in numerical relativity. Of course, we have to solve the Einstein's equation, but now so we know so that how to solve the Einstein equation works. And then so I think that this field is established well. And also we have many good codes for solving the hydrodynamics and the magnetic hydrodynamics and the radiation and viscous hydrodynamics. So then for black hole merger, we only needed to solve the Einstein's equation, but for solving the neutron-star merger, we have to solve the matter equation, but at least for hydrodynamics and the magnetic hydrodynamics, we have many good code. And also, usually neutron-star has a strong magnetic field, and then magnetic field could play a very important role. So that means that we have to solve the also Maxwell equation. But also, we have many good code for this. The last frontier in this field is to solve the radiation transfer equation. Because the radiation transfer equation is just six plus one dimensional equation, and then so it's quite tough business to solve. But still, so we have a significant progress in the last decade, and now we have, for example, M1's approximate radiation transfer solver. Also, so some people are developing a Monte Carlo scheme to solve the to fully solve the radiation transfer equation. But anyway, so I would like to say that also this is a challenging but still a significant progress in the last decade. And also we have a non-powerful computer and also adaptive machine environment and so on. So then, so now we can certainly derive a reliable numerical result, in particular for neutron-star merger. And then why neutron-star merger is interesting and important. I think there are at least four reasons. First reason is that so neutron-star merger is a promising source for gamma ray bursts, short-hard gamma ray bursts, maybe also long gamma ray bursts. And neutron-star merger is predicted to be a promising site for R-process nucleosynthesis, so rapid neutron capture nucleosynthesis. This is the main topics in this talk. And also, neutron-star merger can be a source for the high energy bright source, astrophysical source, kilonovae or macronovae. So this is a nova driven by the radioactivity of neutron-rich matter. And also, neutron-star merger is a very important site for studying nuclear equation state through gravitational detection. And so, anyways, there are four important motivations why we study neutron-star merger. And then what was nice is that in 8 years ago, in GW7017, first neutron-star merger was observed, and then so this shows that all these aspects. Yeah, this is a one-page summary of GW7017 and the electromagnetic counterpart. Anyway, in this event, so first, so gravitational waves are emitted very clearly, and then so from this sharp signal, tidal deformity of neutron star is measured approximately, and then so we got the constraint for neutron star equation state. And then 1.7 seconds later, so gamma ray burst was detected. This is the off-axis gamma ray burst, not the face-on gamma ray burst, but the initial gamma ray burst are detected. And then subsequently, so kilonovae, so radioactive, so shining by radioactive decay, detected significantly. And then so this shows that just neutron-star merger, R-process nucleosynthesis rarely occur. But unfortunately, we still have only one event, so in 10 years. So I'm looking forward to seeing that the next event. But for next event, so we have to prepare. So because after you will find later, so neutron-star merger should have a variety. And then so next event may not be the same as this event, and then so we need a variety of prediction. And in this talk, so I would like to show that really so possible variety of nucleosynthesis and kilonova, the neutron-star merger. So before going ahead, so I would like to summarize the fact is the R-process nucleosynthesis. Anyways, this is the abundance, solar abundance pattern of the elements. So we have a hydrogen, helium, and the light element, and the heavy element, and so on. So for light element, its mass number smaller than the ion formed from the thermonuclear reaction work. Also for a little bit heavier elements could be formed from the quasi-thermonuclear reaction. So I think that this formation, so production process is well known. And for heavier element, with mass number larger than 80, so we believe that these elements are synthesized from the neutron capture. neutron capture for some seed elements. And also in neutron capture element, there are two types. One is a slow neutron capture element, and the other is a rapid neutron capture element. And for slow neutron capture element, so I guess I think that we believe that it's formed, it's produced in the red time evolution star, so intermediate mass evolution star. I think that people have a consensus about this. By contrast, for origin of R process nucleus, R process element is still unclear. And as I already said in the previous slide, so GW T indicated that the neutron star merger is likely one of the major sites for R process nucleosynthesis, but it is still not clear whether the neutron star merger is a dominant site. So it's not very clear. So then, this is the reason why we are looking for the next neutron star merger event in the near future. And then, under such a situation, what should be explored from theory side? So observation of gravitation wave is, of course, necessary, but theorists would like to approach from theory side. And one important and very important observational factor is that the solar abundance pattern is similar to those of the observed metal cluster for R process element. This is a figure from many years ago, but anyway, so situation hasn't changed significantly. This is roughly speaking a solar abundance pattern. So abundance pattern as a function of the atomic number, and there are 6 abundance patterns for metal cluster, and this solid curve, solid line, is a solar abundance pattern, and you can see that for that metal cluster, so abundance pattern for metal cluster is quite similar to solar abundance pattern for each. So this shows that for metal cluster, we could have some universality. So universality or quasi-universality, and this suggests that there would be one major origin. If we have a few, so more than 2 origins, so it's quite difficult to believe, so explain that why we have a universality. So then anyway, so the question is that what is a major origin? And but if a neutron star merger is a major site for the R process element in the entire universe, so this universality has to be reproduced, but it's not very clear. The reason is that there are wide variety of possibility for neutron star merger and after merger evolution process. This is the possible fate of a neutron star merger after the merger. This is a heavy side, this is a relatively light side. And if mass of the total mass of a neutron star, 2 neutron stars is larger than some threshold mass, which depends on the equation of state, then so many numerical relativity simulations have shown that black hole is formed soon after the merger. And if mass of the black hole, if mass of the neutron star is approximately the same, so then the black hole is simply formed. And then if we have a mass asymmetry, disk may be formed around the black hole, because the lighter neutron star can be highly disrupted during the merger. By contrast, if mass is relatively small, so at least temporarily, very massive neutron star can be formed. And then, so because it's rapidly rotating due to the orbital motion, and because it has a strongly magnetized and also should have a effective viscosity, it evolved due to the angular momentum transport and the gravitational emission. And eventually, after the significant angular momentum transport process, so many numerical relativity simulations actually show that the black hole is formed, but after some time. And due to the angular momentum transport process, black hole is surrounded by usually disk like this. And this can be the source of the gamma ray burst. And also, even when total mass is smaller than this threshold mass, we could also have the very long-lived neutron star. So we call it a supermassive neutron star. In this case, even after the some redistribution of the angular momentum, a neutron star could survive. But anyway, so such a neutron star should be the pulsar. So then, so pulsar emit electromagnetic waves and just lose the angular momentum, and for a long time scale, it eventually collapses the black hole. But anyway, so there are a variety of possibilities depending on the mass of the two neutron stars. So then, so it's not very clear whether for every case neutron star merger can reproduce the solar abundance pattern in the ejector. So this is the reason why we need a numerical relativity. This is also the case for black hole neutron star merger. For this case, so path is quite simple. So if black hole masses are relatively large, in such case, so neutron star tidal disruption never occurs. And then so black hole simply swallows the neutron star and nothing happens. It's not very interesting. By contrast, if black hole masses are relatively low, or black hole spin is very high, in such case, neutron star may be tidally disrupted. And then, so in this case, also again, so we have a black hole plus disk system, and this can be interesting source of GRB and mass ejection and nucleosynthesis. But anyway, so also in this case, there are freedom for the black hole spin and mass relation and so on. So then, so so mass ejection and the GRB property are not trivial. So actually, so again, so we need to perform a lot of simulation for this. And actually, so we have been performing such a simulation the last decade, and then so we got some information that I would like to tell you that what we have known about this. So this is the basics of the neutron star merger and mass ejection. Anyway, so after the merger, initially, matter is ejected by shock heating and tidal disruption. So we call such a ejector the dynamical ejector. And then, so as I already explained, so typically we have a central object and a disk, black hole neutron star disk. And because the neutron star is magnetized, disk is magnetized, and then so we believe that in the disk we have a magnetorotational instability, and effective viscosity is induced, and then so disk evolve due to the viscosity, and then gradually expand and heat by heating, so matter is ejected. And so we call such a mass ejection as a post-merger mass ejection. So anyway, so what is important is that there are two steps. One is a dynamical mass ejection, the other is a post-merger mass ejection. This is the key in my talk, today in my talk. And time scale is completely different. So for this, so time scale 10 milliseconds, but for this time scale is 1 second. And of course, in addition to this, if black hole is formed, then so gamma ray burst is likely to be. And in today's talk, so I focus on the mass ejection and the nucleosynthesis, and for mass ejection and nucleosynthesis, weak interaction. So neutron electron interaction, for example, determine the property of ejector, and this is quite important. And specifically, in the following, I often refer to the electron fraction defined by the proton number divided by nucleon number. This is a key for nucleosynthesis, and I often say that the Y is, so then please remember the definition of this. Anyway, so this is a figure why Y is important. This is a nucleosynthesis calculation by Wanadro 11 years ago. So he analyzed the nucleosynthesis pattern by taking the neutron star merger simulation as a data. And then he found that anyway, so if YE, so Y is low means that the neutron richness is high. So then heavy element is synthesized. Right? This is the heavy element side, and this is the low, less heavy element side. And if Y is 0.15 or 0.09, so then heavy element is efficiently synthesized, while lower mass element is not synthesized. On the other hand, this component can explain the heavy element in the solar abundance pattern. On the other hand, if Y is close to 0.5, so proton number, the neutron star number approximately the same, so then only low mass element around here, the synthesized, this one. So his result shows that to reproduce a solar abundance pattern by one event, ejector has to have a variety of components, variety of Y components. So in a sense, we need some miracle to reproduce a solar abundance pattern. So we need appropriate blending of the different Y elements. So then the question is that in neutron-star merger, whether it's possible or not to have such a good Y blending. And then this is the question. So is it possible to have a good blending for multiple Y component injector? And then answer is yes, but only for restricted case. So I'll show you the reason. Anyway, so I say that we have two steps. First step is dynamical mass ejection, and the next step is post-merger mass ejection from the disk. And numerical relativity simulation have been done significantly in the last decade, and then at least for dynamical mass ejection, I think that we understood well. So this is a summary. So for dynamical mass ejection, mass is for neutron-star merger, neutron-star merger, mass is between 10 to minus 4 to 10 to minus 2 typically. And what is important is for total mass case, for which remnant neutron star is long-lived. Mass is relatively small, 10 to minus 3 solar mass. By contrast, for high total mass case, it can be quite high, 1% solar mass. And the electron fraction can be a wide variety. So remember that the neutron star has only low Y component, less than 0.1, but after the merger, high Y component can be produced. The reason that at shock heating, temperatures increase, and in such a situation, Y can be increased. And this is quite suitable for ARC to get a wide variety of Y components. And also, velocity of ejector is quite interesting. Typically, 20% of speed of light, but can be very close to the speed of light. But it's not that related. Also, many simulations have been done for black hole neutron-star merger, in particular by François Foucault and Kyoto. And I think that also this process has been well understood. And in this case, only tidal force is a main mechanism of the mass ejection, and then anyway, so depending on the black hole spin and mass ratio, mass can be changed significantly. Zero means that no tidal disruption, just neutron star swallowed with the black hole. And in this case, we don't have any significant shock heating effect, and then electron fraction is always low. So it's original value of neutron star. So this is quite different from the neutron-star merger. But still, it's suitable for producing heavy elements in the ejector. And also in this case, average velocity is relatively lower than the neutron-star merger. I think that for dynamical ejector, we understood well the process and quantitatively, and then I think that this conclusion will not change significantly. But by contrast, for post-merger mass ejection, because it's more complicated, and then well, conclusion could be changed in the future. But I will show you that the current our conclusion. Anyway, so the key is that the neutron star is magnetized, and then remnant should be also magnetized. And then, so in the presence of magnetic field and differential rotation, so we could have many image instabilities like MRI and Kelvin-Holmes instability. And then, as a result, mass ejection is induced, as I already said. And there are two channels. One is turbulence and effective viscosity. So due to the presence of turbulence, effective viscosity are induced, and then so matter is ejected by viscous force. And in addition, so we have a purely MHD force. For example, like a magnetic centrifugal force effect, something like this. And then, so by these two effects, post-merger mass ejection occurs from the disk. But anyway, so already so it's quite complicated because we have to take into account the magnetic field in this case. And anyway, so in the last 5 years, we have had a lot of simulation about the detailed simulation for this. And now, so we found that the ejector mass depends on the remnant. So for example, if a remnant is a quite long-lived neutron star, and if we have a long-lived neutron star at the center for fairly long time scale, for more than 100 milliseconds, so then so ejector mass could be quite long, quite high, 5% to 10% of solar mass. By contrast, if a black hole is formed soon after the merger, so then so ejector mass could be very low compared with this one. The reason is that in this case, so central neutron star can be just a reflector. So then, so we could keep the high mass disk. But in this case, black hole is formed soon, and then so disk matter is swallowed into the black hole, and then so ejector mass becomes small. So then this is the reason. And the other important thing, so the main target is just YE, and so YE is determined by complicated process, but anyway, so weak interaction is the key. So I'd like to explain that how YE is determined. So this is just a one-page evolution process of the disk around the black hole neutron star. Anyway, so as I said that the disk is magnetized and the viscosity is induced, and we have also magnetic field. And but here we focus on the viscous effect. Anyway, so due to the viscous effect, so disk gradually expands. Also, at the formation, disk is quite very hot and high temperature. And specifically, so this maximum temperature is higher than 3 MeV. In such case, so neutron cooling is quite efficient. So then, so even if viscosity make a heat, then so it's consumed by the neutron cooling. Then so in such situation, so neutron carries energy and then mass ejection is suppressed. This is the case for high temperature and high density disk. But viscosity is present and the mass ejection is prohibited, but because of the viscous angular momentum transport, disk gradually expand and the density gradually decrease. And then so because of the decrease of density due to the adiabatic expansion, temperature decrease. And then so because the neutron luminosity is a steep function of temperature like this, then so neutron luminosity can drop very significantly. And then so eventually viscous heating completely overcomes the neutron heating. And then in such situation, matter is ejected from the system. This is a so very rough explanation of the post-merger mass ejection. But anyway, so for this, so it takes a long time. So 1 second, roughly speaking, 1 second. Then so for simulation work, which is a long-term simulation, but such simulation has been done in the last decade. And then this is one example. In this simulation, so 3 solar mass black hole and 1.1 solar mass disk is considered. It's better to continue. So initially, due to the viscous angular momentum transport, disk gradually expanded, but no mass ejection. But after 1 second, mass ejection is induced. The reason is that viscous heating overcomes the neutron cooling in the rate phase. And the other interesting thing is that matter is ejected, but color is always green or yellow. Green or yellow is that Y is around this. So this means that the rho Y component is not ejected in the post-Martian mass ejection. What is the reason? And how Y over disk ejected is determined. So this is determined completely by the weak interaction. So as I said that for high density and for high temperature, initially so disk is a high density and high temperature. So temperature is higher than 3 MeV and the density is 10 to 11 and 10 to 12 gram per cubic centimeter. In such situations, so beta equilibrium is established. So beta equilibrium is this one. So proton absorbs the anti-neutron to be a neutron, and anti-neutrino to be a neutron plus a positron. So and this one. This is established for high density and high temperature situation. But then so Y is determined by the this is chemical potential. This equality of chemical potential. So this is small, so because the neutron is emitted, and then so this is essential equality. But here, what is important is that for high density, neutron degeneracy is quite high. So this is quite high. So then, so to establish this equality, this has to be high. This is the reason so high density matter becomes very neutron rich. But this expands gradually, and then so temperature decrease, density decrease, and this equilibrium is not established gradually. And then finally, if temperature, maximum temperature is lower than 3 MeV, weak interaction completely decays. The reason is that, for example, neutron cross-section is proportional to the energy square. So that means that if temperature drops, then so cross-section becomes smaller, and then so weak interaction decays. And then in such a phase, Y is completely fixed, and then matter is ejected. So this is a mechanism how Y is determined. And then so, but to determine the exact Y value after decoupling, so we need a numerical simulation. But in the last 5 years, so we performed a lot of simulation, and then so we found that the typical value is Y equals 0.3. 0.3 is much higher than the 0.1 for neutron-star. Then so this is in a sense a summary for the Y component. So as I said that there are two components. One is a dynamical ejector, and the other is a post-merger ejector. So dynamical ejector has can have a low Y component, but also can have a high Y component. On the other hand, for post-merger ejector, Y is quite relatively high. And this is a dynamical ejector component. This is a post-merger ejector component. Anyway, what is important is that there are two components. And the other important thing is that mass is quite depends on the type of merger. In this case, so mass is relatively low, and then so lifetime of the remnant neutron star is long. In such case, so post-merger ejector is much higher than the mass is much higher than the dynamical ejector. But if lifetime of the post-merger remnant is shorter, then in this case, so mass can be comparable. So this is a quite clear contrast. And then, so yeah, in this case, so yeah, more than 50 times higher. But in this case, mass is comparable. So yeah, anyway, so what is important is that the mass ratio by dynamical and post-merger ejector depends significantly on the lifetime of the remnant neutron star. And then under this condition, we perform the nucleosynthesis calculation, and this is the result. And this is for long-lived neutron star case, and this is the short-lived neutron star case. And then, so for this case, so because we have a lot of post-merger ejector for quite relatively high Y component, and then we have a low mass element. We have a much larger low mass element than the high mass element. So here, so dot shows the solar abundance pattern. So then, so for this case, it's quite difficult to reproduce a solar abundance pattern. But by contrast, if a dynamical mass, dynamical ejector mass and the post-merge ejector mass is comparable, so we can approximately reproduce a solar abundance pattern. Very good. So then, so anyway, so the conclusion for this figure is that this is not suitable for reproduce a solar abundance pattern. Too much post-merge ejector. But in this case, good braining is established. So then I have prediction. So as I show, only when the remnant of binary neutron-star merger collapse the black hole in a short time scale, universality, solar abundance pattern's universality can be reproduced. So suppose that the neutron-star merge as a main site for the R process nucleosynthesis. So long-lived massive neutron-star formation should be a minority. So in other words, in the future, in case that many long-lived neutron-star formation are observed by gravitational waves, for example, so neutron-star merger shown of the R process nucleosynthesis should be reconsidered. So then this is a prediction. But note that, as I already said, that the post-merger process is highly complicated because the gravity, weak interaction, magnetic field, or everything coupled. So then, so this conclusion may be modified in the future. But anyway, so currently this is a prediction. So anyway, so this is also prediction. So anyway, so we have a wide variety of possibility, but this possibility should be minority. Otherwise, we can't reproduce a solar abundance pattern. But until, so this is a result until about 5 years ago. But in the last 5 years, the situation has been changed. So we can perform a self-consistent simulation. Then, so in the last 15 minutes, I'd like to talk about the latest numerical simulation results. But anyway, so as I already said, that in this problem, there are 3 important time scales. So dynamical mass ejection time scale is quite short. Post-merger mass ejection time scale is quite long, millisecond. And also to reduce, for example, short gamma ray burst, we have to also follow the system by 2 seconds because the typical duration of a short gamma ray burst is about 1 second. Also, anyway, so we need more than 1 second simulation. Also, physics is complicated. So, in particular, for post-merger evolution, we have to take into account the general relativity, of course, and the magnetohydrodynamics is also important, and also weak interaction is the key for determining the nucleosynthesis. So, anyway, so at least 3, and also equation state is important. So then all 4 force in nature plays an important role in this problem. So it's quite challenging, but now it's possible to do. So then, so I'd like to show you that some interesting result. Actually, we have published a couple of papers about this. And then, so what is a found? Anyway, so post-merger process is self-consistently clarified. And in the post-merger process, magnetic field is amplified by winding and MRI in the disk after the merger. This is well reproduced in these simulations. And then we found that turbulent viscosity and also dynamic in these simulations. And this is the key for post-merger mass ejection. And also what is nice is that after the development of a turbulence in the disk, eventually magnetic field that penetrate the black hole is formed globally. So I mean that the global magnetic sphere is around the black hole is established after this turbulent and the dynamic process. And then so in some cases, we can reproduce a jet, and that can be responsible for the JRB, via black hole magic mechanism. So I'll show you some examples. So first, so I'll show you a neutron-star merger for this case. So typical mass case. In this case, so after the merger, black hole is formed. About 20 milliseconds after the merger. Yeah. Anyway, so this was a simulation 3 years ago. And this is just for 1 second simulation, but for 1 second simulation, it took 1 year, so it's quite heavy simulation. Okay, so this is the rest mass density and the electron flux and the magnetic. But anyways, after the merger, dynamically matter is ejected, and at the center, in this case, black holes are formed quite soon, and then the disk is surrounding the black hole. And then, so inside the disk, magnetic field is amplified gradually. And then, so this fluid behave as a viscous, effectively viscous fluid. And then, due to the angular momentum transport, matter is ejected gradually, and in the late phase, temperature is quite low, and then so mass ejection is enhanced. Then, so we have a clear mass ejection from the system, and at that 1 second. So anyway, the key result is that we found that the mass ejections are indeed occurs in 2 stages, dynamically and post-merger mass ejection. And this is the Y distribution of ejector. So this is quite similar to the previous part of 2D plus 3D simulation. And then this is a dynamic ejector. This is a post-merger ejector. We have 2 components. And for this case, this component is quite good to reproduce a solar abundance pattern. And also, this is this similar simulation is also can be done. Could be done for black hole neutron-star merger. So in this case, this is the density magnetic field and magnetic pressure divided by the rest mass density, and just ignore this one. So in this case, neutron-star is tidally disrupted at the merger, and then so we have a black hole on the disk. And then due to the MRI and subsequent dynamo, we have a viscosity, and then so disk expand gradually, and then finally mass ejection. And also in this case, what is nice is that after the enhancement of the magnetic field strength, then eventually we have a magnetosphere that penetrates the black hole, and then so we found a jet-like structure like this. So for this region, so magnetic pressure is much higher than the rest mass density, and we can interpret this as a jet. Also in this case, so we have a clear 2 component, dynamical ejector component and the post-merger ejector component. Also, this is very nice to reproduce a solar abundance pattern. For this case, we performed a nucleosynthesis calculation by Masaru. And gray shows a total. Total is quite good agreement up to here with the solar abundance pattern. But the gray is composed of by 2 components, post-merger component in red and dynamical component by blue. So then, so by adding 2 components, this pattern is well reproduced. But then, so previously, so black hole neutron-star merger maybe are believed as not good site for so to reproduce a solar abundance pattern. But by adding 2 components, so we find that it's a very good also candidate to reproduce the solar abundance pattern. And then prediction is that the black hole neutron-star could be also very good to reproduce the solar abundance pattern. And finally, so this year, so we published new neutron-star merger simulation. In this case, total mass is a little bit higher than previously. And in this case, so then so black hole is formed soon after the merger. But this is quite nice to jet launch. Anyways, after the merger, matter is ejected dynamically. This is a small scale and large scale. The matter is ejected dynamically, and around the center, black hole surrounded by disk is formed. And then, as I already said, that in the disk, we have a MRI and turbulence and dynamo, and the magnetic field is amplified, and then so post-merger mass ejection is induced. But at the same time, also, we have a magnetic field penetrating a black hole. So you will see the magnetic field later. So later so magnetic field penetrating the black hole to establish some dense or Z-like structure changes. But anyway, so to have this kind of structure, we have to a little bit wait for a while because we need a time for enhancement of magnetic field in this. Anyways, I think that this is the best movie so far from us. Looks very nice. And then, so this is well, summary for time scale of post-merger process. Anyway, we have after dynamical mass ejection, which occurs within 10 milliseconds, we have a post-merger phase, but the lifetime of remnant neutron star depends on the total mass and the neutron star equation state. This is quite uncertain. But dynamic growth time scale and anyway, so irrespective of the central object in the disk, dynamo action occurs and then so magnetic fields are amplified in the disk. And it takes at least about a few hundred milliseconds. And then, so after this amplification, we have post-merger mass ejection and could be jet and gamma reverse. Yeah, this is well, in a sense, a conclusion from our simulations. And then, based on these results, I would like to interpret that what happened in 2017. The following is the observational information. So anyway, so in this event, so GRB was observed. That means that indicates that the black hole is likely to be formed eventually after the merger. And kilonova is quite bright. In this case, what is important is kilonova is quite bright. And then, so according to these people, so ejector mass is likely to be more than 5% of solar mass. And in this case, by the gravitational wave observation, we find that the total mass is roughly 2.75. And also by gravitational wave observation, so neutron star radius is between 11 and 14 kilometers, roughly speaking. And that means that the EOS is not extremely soft. Could be not extremely soft and not extremely stiff. So moderately stiff. And then, so it's consistent with this scenario. So initially, neutron star is formed, but black hole will be formed later. And then, based on this information, we try to interpret this system. So first, so we try to interpret this result using the some numerical result, which in which black hole is formed quite quickly after the merger. So in this case, so in this numerical relativity model, black hole is formed within 20 milliseconds after the merger. But in this case, so we didn't find that a lot of ejector. Then as a result, so this is a light curve, volumetric light curve, and this is a volumetric luminosity from the observation. And in this case, it's quite difficult to reproduce observational result, simply due to the lack of the total ejector mass. But by contrast, if neutron star remnant is long-lived, we could have a quite high ejector mass. And then in such case, so depending on model, so some fraction appear, but roughly speaking, with this kind of mass, it's possible to reproduce so luminosity curve. So then, so this shows that well, so it's likely that GW7270 is likely to produce a relatively long-lived remnant neutron star. Then, so the following is a guess for timeline. Anyways, at 0 millisecond merger occurs, and then massive neutron star is formed finally initially, and dynamical mass ejection occurs, and then so mass is less than 1%, roughly speaking, a few percent of solar mass. And then from this heavy element is synthesized. And then perhaps 100 milliseconds, after 100 milliseconds, 200 milliseconds, this remnant collapsed the black hole surrounded by this. And the disk, so we have a turbulence, MRI, and dynamo, and then eventually magnetic field is amplified, and the black hole magnetic sphere should be established, and just a jet and black hole jet via the black hole transit process occurs. Also, post-merger mass ejection. And for post-merger mass ejection, so required mass is about this. This is the reason why we need a relatively long-lived neutron star. And then disk expand and post-merger mass ejection finally inactive. And also after the post-merger mass ejection becoming active, so that means that the disk expands significantly. So then opening angle for jet become wider and wider, and then perhaps due to this, GRB luminosity drops. This is a very naive picture. And then based on this, I would like to interpret 1.7 seconds. So anyway, after the merger up to the GRB starts, so it took 1.7 seconds. And as I said, that the lifetime of remnant neutron star is about 0.1 second. And to amplify magnetic field in the disk by dynamo, we perhaps need a few seconds. So say 0.3 seconds. And that means that so at 0.4 seconds after the merger, jet start launch in this case, so in my assumption. And then to penetrate the dynamical ejector head for jet, so then this is the estimated time. So this is here, so I assume that the velocity of dynamical ejector head is about 2/3 of the speed of light. Then to penetrate the jet, so it takes about 1.2 seconds, and then in total, so 1.6 seconds. So then this is one interpretation which I like. But anyway, this should be tested by the next event, and this is the reason why we are looking forward to see in the next event. But anyway, the conclusion. I think that I hope that you found that the numerical relativity is playing an important role in interpreting observational results, in particular gravitational and electromagnetic counterparts. And so as I showed that the simulation of the relevant physics is now feasible, so it's great for me. And then I gave us 3 predictions. So one is the formation of long-lived neutron star should be minority. If this is not the case, so R process nucleosynthesis hypothesis from the neutron star merger hypothesis should be rejected. So, and the prediction 2 is that the black hole neutron star is also very good site to reproduce a solar abundance pattern. And prediction 3 is that in GW17, so are likely to form a relatively long-lived neutron star. And this shows that the neutron star is not very soft, it's consistent with the measurement of the tidal deformability. Thank you very much.
At the late stages of your simulation, the disk has expanded. It's no longer accreting. The magnetic fields are dying. What is the very long time evolution of that disk like?
So disk expand, and then I didn't say anything about this collimation of magnetic field. So but is achieved by the in a sense torus or disk, and this expand. So then magnetic field should expand gradually, and then eventually we have a reconnection at the equatorial plane, and then magnetic field will be lost. So this is my guess, and then I guess that this occurs after a few seconds, and then short GRB is so then this is the scenario.
I have one question about the first prediction. You stated that to reproduce the R process, you need the black hole will form promptly.
Yeah.
And then the prediction is that the short GRBs will be
not promptly, just
almost promptly,
yeah,
but not to generate a jet, and most mergers will not produce short GRBs. This is consistent, I think, with what we see in the neutron-star binaries in the galaxy, that they have the same mass ratio, so you don't expect. So I think it's consistent in this sense, but I guess my question is, when you're considering the rate of beaming corrected rate of short GRBs, I think with what we know now from gravitational waves about the rate of neutron-star mergers, I think they're roughly consistent. So the question is, how is it?
Used to be roughly consistent, but after 04, event rate of neutron-star merger dropped by 1/3. So then, maybe it's marginally consistent, I guess. So in that sense, of a lot of neutron-star merger event in the 04, I'm wondering that whether it's really consistent or not. Actually, so I asked Kenta Hotogezaga to write the figure for the consistency. So then, yeah. So merger rate is observational rate. The gravitational wave is a little bit lower than the merger rate, so predicted from the galactic pulsars. So let's see what happens. Maybe 05, maybe. So there could be many neutron-star mergers.
And one another small question about one of the last slides.
Yeah.
You calculated what is the time it takes the jet to propagate within the ejecta.
Yeah.
Did you? I'm not sure. Did you consider here relativistic effects, because the black hole time is not the same as the observer time, and the black hole is okay. Thank you.
Yes, this is estimated in the Masaru. So then, yeah. It was taken into account. Yeah.
Sorry. So Shibata-san, you said that if in future light will observe a lot of long-lived neutron star mergers, then the whole picture need to be changed. Then I want to ask, like, in what physics needs to be reconsidered in this case? Would that be the nucleosynthesis rate for these heavy elements, or something else?
Yeah, in this case, perhaps we have to consider another major source for our process nucleosynthesis. Yeah, so, but Brian has been doing this kind of business for a long time, and then so maybe it could be possible. So I'm not sure, but yeah, but anyway, so also the other possibility is that so any post-merger process is highly complicated, and then so another possibility is that in the future. Another possibility in the future is that our simulation was wrong. This can be possible. Also, yeah, for example, nowadays several people is seriously considering the Newton oscillation. And then well, I'm not sure that what happens, but Newton oscillation may play a role, and then conclusion may be changed. For example.
Question. You have the beautiful viscous hydro simulation. So how do you model your viscosity in neutron star simulations?
It's a very simplified viscous hydrodynamics formulation from the Israel's chart. In the Israel's chart, they took into account not only viscosity but also thermal conduction, and also other process in the viscous hydrodynamics. But here, I take into account only just shear viscosity. Yes.
If we don't get another multi-messenger observation, is there anything you could hope to learn from the gravitational waves alone, perhaps post-merger signals from the neutron star? Are there scenarios where we can still help here without
So no gravitational waves.
Only gravitational waves.
Only gravitational waves. Only gravitational waves. So perhaps the most important thing is that to detect the post-merger gravitational wave form. So with about 3 kilohertz, and that could change completely the situation. So I'm looking forward to this, but this is likely to happen after my retirement. I'm so unfortunate. But obviously, so since third generation detectors, detection of the post-merger gravitational wave is very important, I think. Then situation will be changed significantly. Question state will be constrained quite significantly.
Right. So, in the absence of gravitational wave triggers, there's been now this rise of people looking for essentially excess infrared emission after things from Einstein probe or short GRBs. That appears to be the more productive path to finding these things right now. So, but a common approach that people use is that they look for this long-lived infrared emission as a signature of a kilonova. Kilonova actually occurring, but I wonder if from your simulations for the case where there is long-lived neutron star, you said that the predictions were that they would produce not as much heavy elements, in which case you would not quite expect the long-lived infrared signature. Do you think observers are missing out on potential actual counterparts because they're not red enough? Yeah. Like, what would the electromagnetic signatures for those events look like? Would they have a long-lived infrared source if they don't produce as much heavy R process elements?
So you are, what do you mean that anything in the absence of a lot of heavy element, and then so lanthanum is quite absent, and then so could be blue. So
yes, and in which case we would think it's a supernova, not a kilonova.
But still, so maybe so. Well, it's not very easy to answer. But still, so we could have a random. I have never considered that how significant is this, but only still 10% of solar abundance pattern, but could make us still relate. And also here, secondary pulsar element can contribute to the opacity. So then, opacity is not very low. So if opacity is if elements are composed only from the ion, so opacity is kappa equal 0.1. But in this case, perhaps the opacity could be still so about order of unity. So I guess Then so I have never considered. So this is my guess.
Sorry. Can you remind me of the initial magnetic field configuration in the simulation?
In this case, so just we input the toroidal magnetic field inside the star. In this case, so inside the neutron star, we put the toroidal, so just dipolar type magnetic field initially. But
and what's the strength initially?
Strength is quite high, so 10 to 15 Gauss at the center. Otherwise, so it's impossible to resolve the MRI. But what is the point is that after the merger, black hole is formed and the disk is formed. But in the disk, magnetic field is much weaker because most of our matter is swallowed into the black hole.
Right. Okay. Thanks.
So you're arguing that there should be almost no long-lived neutron star events on the basis of reproducing a solar abundance pattern at low metallicity. But there aren't a huge number of samples of measured low metallicity stars. And kilonova are correspondingly pretty rare. So how tight is that constraint? Long-lived must be no more than 10%, no more than half.
10% would be fine because actually, solar abundance patterns so low mass side is could be quite dilute. So I didn't have a figure, but for example, for Honda star, it's our process element star, but still so Honda star has quite a lot of robust R process elements. Then so my bet is about 10%. 10% is fine, but
More than
100%
that.
is not very good. It is fine.
I wanted to ask a question, I presume. Is that okay?
Yeah.
Hi, Masaru. Thank you for the
Yeah.
nice talk. I wanted to ask your opinion on whether you think the simulations are converged with respect to the lifetime of the hypermassive neutron star, because while I agree you can resolve the MRI if you start with a fairly strong magnetic field, and the result may be relatively independent of that assumption, in the center of the remnant where the angular velocity is rising and the MRI is stable, there could be other forms of angular momentum transport, like the Taylor instability, that are notoriously hard to resolve, even in directed simulations. And so I'm wondering if you have any thoughts as to whether you think the angular momentum transport in the very core of the star could be influencing the lifetime, if you think we're converged with the life.
You're right, you're right. So then, so yeah, you're right. For long-lived neutron star case, so yeah, Taylor instability is likely to play important role. And so yeah, our colleague in AI is working in this kind of a problem, but our time scale could be quite long. So then, yeah, you're right. It's not. I can't answer right now. So whether we can resolve such a process. So actually, so well, we found that our resolution, even if our resolution, in the best simulation, the resolution in the best simulation in our group is that, for example, at the center, grid spacing is only 15 meters, something like this. But even for such case, it's not very easy to resolve the Taylor instability. So yeah, you're right. So yeah, it's not still so. We still have a.
If it's very, yeah, if it's very slow, then maybe it's not relevant. But at the same time, that's the only thing operating in the center, and so it's. I think it's hard to say whether it's
Yeah, you're right. You're right. So, yeah, I completely agree with this. But it's next. It's the next target. For example, Kenta Kiuchi is working on this right now. So, but I'm not sure whether we have a success.
Okay. All right. Thank you.